How did everything begin? This profound question bridges both science and philosophy, urging you to consider the very nature of being and the enigmatic instant our universe was born. The notion that all of reality emerged from an absolute void challenges our daily perceptions, inviting you to ponder the incredible moment the cosmos ignited, bringing forth the elementary particles that would eventually compose the world we know. Contemplating this topic extends beyond scientific curiosity, touching upon the meaning of existence, the essence of non-existence, and the potential processes through which the universe could have sprung from nothing. In this journey, I will investigate these foundational inquiries from the perspectives of physics, the subatomic world, and cosmology, where researchers use mathematical frameworks and experimental data to pursue these immense mysteries. At the very center of this scientific quest, however, lies an even more fundamental challenge. What does it truly signify for something to materialize from a complete vacuum? And how can our physical laws account for the birth of a cosmos from a state where space, time, and matter simply did not exist? The physics of the microscopic world delves into the smallest constituents of reality, exploring the elementary particles that are the bedrock of all that exists and the forces that mediate their interactions. This subatomic domain operates under the principles of quantum theory, a framework that unveils a reality starkly different from the macroscopic world governed by classical mechanics, presenting a realm that is both fascinating and counterintuitive. The central purpose of particle physics is to determine the composition of the universe and understand its most fundamental operations. Experts in this area investigate particles like quarks, electrons, and neutrinos, which are the essential components of atoms and, by extension, all matter. These particles are so infinitesimally small that their properties and behaviors challenge our conventional understanding of space and time. You can imagine the difficulty of this work by picturing an attempt to grasp a city's complete architecture by only examining individual grains of sand through a microscope. It requires looking at objects billions of times smaller than anything the human eye can resolve. One of the most significant accomplishments in particle physics is the development of the Standard Model. This theoretical framework successfully describes the fundamental particles of our universe and all their interactions, with the notable exception of gravity. The Standard Model outlines four fundamental forces: the electromagnetic force, responsible for light and magnetism; the weak nuclear force, which governs certain types of radioactive decay; the strong nuclear force, which holds atomic nuclei together; and gravity, the force of attraction between objects with mass, which has yet to be integrated into the model. Despite its incredible success in predicting and explaining particle behavior across innumerable experiments, the Standard Model is not the final theory. Scientists are actively seeking a more comprehensive model that can successfully incorporate gravity and also solve the puzzles of dark matter and dark energy. These mysterious components are believed to constitute the vast majority of the universe's mass and energy, yet they have so far evaded all attempts at direct detection. Progress in particle physics relies on extraordinarily sophisticated technology, including massive particle accelerators and detectors. These instruments propel particles to velocities approaching the speed of light before smashing them together, which allows scientists to study the interactions and the new particles that are created. The Large Hadron Collider, situated on the border between Switzerland and France, stands as one of the most powerful such facilities ever built. It was at this very facility in 2012 that researchers confirmed the existence of the Higgs boson, a particle long predicted by the Standard Model and crucial for explaining how other particles acquire their mass. This discovery represented a major leap forward in our understanding of the subatomic world. And while the field is incredibly complex, it is ultimately propelled by a straightforward yet profound question. What is reality fundamentally made of? The pursuit of an answer has not only spurred revolutionary scientific insights, but also led to transformative technological advancements. For instance, the World Wide Web was initially conceived at CERN, the European Organization for Nuclear Research, as a tool to help scientists share data more effectively. As we probe deeper into the universe's secrets, we continue to uncover remarkable and intricate connections. The powerful synergy between cosmology and particle physics is becoming increasingly evident. Cosmology, the science that studies the universe's origin, evolution, and structure, finds an indispensable partner in particle physics, which focuses on the fundamental building blocks of matter. This collaboration is forging new pathways to understanding not just the cosmos's composition, but also the very mechanisms of its birth and development over billions of years. Central to this partnership is the Big Bang theory, a cornerstone of modern cosmology. This theory posits that our universe originated from a state of extreme heat and density, approximately 13.8 billion years ago, and has been expanding ever since. Particle physics provides crucial insight into this primordial era by examining how particles behave under the immense energies that were present in the first moments after the universe's creation. By recreating these conditions on a small scale, inside accelerators like the Large Hadron Collider, researchers can effectively study the processes that unfolded during the infancy of the cosmos. One of the most captivating areas where cosmology and particle physics meet involves the study of dark matter and dark energy. These enigmatic substances are thought to constitute roughly 95% of all the mass and energy in the cosmos. Dark matter is hypothesized to be composed of particles that do not engage with electromagnetic radiation, which makes them invisible and only detectable by their gravitational pull. In contrast, dark energy seems to be the driving force behind the universe's accelerating expansion. Particle physicists are actively hunting for the potential particles that could make up dark matter, employing a combination of deep underground detectors and advanced space observatories. Cosmologists then incorporate these discoveries into their models to better understand the universe's large-scale structure and evolution. The exploration of the cosmic microwave background, which is the residual heat from the Big Bang, provides a powerful illustration of this collaboration. This ancient radiation gives us a snapshot of the cosmos when it was merely 380,000 years old, long before any stars or galaxies had formed. By examining the tiny fluctuations in the temperature of this relic radiation, scientists can deduce how matter was distributed in the early universe and gain insights into its fundamental properties. This research helps refine theories about elementary particles and forces in both scientific disciplines. This collaborative approach has not only deepened our comprehension of the cosmos, but also posed new questions for established theories. For example, conflicting measurements of the Hubble constant, which describes the speed of cosmic expansion, hint at the existence of new physics beyond the Standard Model of particle physics or the lambda-CDM cosmological model. Such inconsistencies fuel the ongoing quest for a more comprehensive theory that could unite the principles governing the universe at its grandest scales, with the laws that dictate the behavior of its smallest components. To delve deeper into this junction of cosmology and particle physics, we must look at the fundamental interactions of nature. These forces act as the universal rule book for the cosmos, defining every interaction from the clustering of galaxies down to the behavior of quarks, and understanding them is key to explaining everything from planetary orbits to the stability of matter itself. Gravity is likely the interaction you are most acquainted with. It's the force that anchors us to the Earth and orchestrates the movements of planets, stars, and entire galaxies. Despite its pervasive presence, gravity is actually the most feeble of the four fundamental interactions. Its strength, however, operates over immense distances, effectively holding the fabric of the universe together. The gravitational pull between two objects is determined by their masses and the distance separating them, a relationship first formulated in Newton's law of universal gravitation. Our perception of gravity was completely transformed by Albert Einstein through his general theory of relativity. He revealed that it isn't simply a force pulling masses together, but is instead a direct consequence of the warping of space-time by massive objects. You can visualize this by imagining a bowling ball on a taut rubber sheet. It creates a dip that causes nearby objects to roll toward it. This is precisely how gravity dictates the paths of planets, and even bends the light from distant stars, though it is just one of the four forces that shape our reality. Next, let's turn to the electromagnetic force, which, if we set aside the nuclear realm, is the most prominent in our daily lives. This force governs the interactions between electrically charged particles like protons and electrons, and it is behind everything from lightning and magnetism to the very light we see. At the particle level, it is thousands of times more powerful than gravity. Without it, stable atoms, chemical reactions, and even the neural signals in your brain would be impossible. I often contemplate how this single force enables so much of our world, from the technology in your smartphone to the vibrant colors of autumn leaves. It functions like an unseen adhesive, binding our world together at the molecular scale. If you've ever questioned why a magnet pulls a paperclip toward it, you are witnessing electromagnetism at work, a constant reminder of how deeply we rely on these foundational laws of nature. Then we have the strong nuclear force, which is the undisputed champion of strength, though it only functions across the incredibly short distances within an atom's nucleus. It is responsible for binding protons and neutrons together, overcoming the powerful repulsive force between the positively charged protons. If this force didn't exist, atomic nuclei would fly apart, and the atoms that make up everything you know would not be possible. It also confines quarks within protons and neutrons, laying the very groundwork for all matter. You can think of the strong force as a minuscule but immensely powerful lock that holds particles together, without which the entire structure of the universe would disintegrate. Scientists calculate that this force is 100 times stronger than electromagnetism on its own scale, which helps to explain the colossal energy unleashed by atomic weapons. It truly is the titan among the fundamental forces, ensuring the stability of the material world. The weak nuclear force might sound underwhelming by comparison, but it is indispensable for processes like radioactive decay and the nuclear reactions that power the stars, including our own sun. Operating over distances even shorter than the strong force, it has the unique ability to transform one type of particle into another, such as when a neutron decays into a proton and an electron. It is, in essence, the universe's quiet alchemist, forging new elements in the hearts of stars. Without the work of this subtle force, the heavy elements required to form our planet would never have been created, and life itself might never have arisen. I find myself wondering what would happen if this force were just a bit weaker. Stars would burn at a different rate, and the fundamental chemistry of the entire cosmos would be irrevocably altered, underscoring the delicate balance that allows for our existence. Astronomers report that the Sun generates trillions of neutrinos every second through weak nuclear interactions, and these particles are currently passing through you without any effect. All of these fundamental forces, gravity, electromagnetism, and the strong and weak interactions, are intricately woven into a grand cosmic fabric that spans from immense galaxies to the most minuscule particles. Physicists aspire to formulate a unified theory, often referred to as the theory of everything, that would elegantly integrate them into a single cohesive system. While this theory remains a captivating but elusive goal, the pursuit of it consistently fuels new and exciting discoveries. Let's now venture deeper into the world of elementary particles, which are the fundamental building blocks of everything in our environment, from a droplet of water in your glass to far-off planets. In physics, the Standard Model acts as our roadmap to these fundamentals, organizing them into categories of quarks, leptons, and the bosons that mediate the forces between them. You can envision it as a kind of recipe for the cosmos, where every single ingredient is assigned a distinct and essential function. Quarks are the foundational units that construct protons and neutrons within the atomic nucleus. They exist in 6 varieties, or flavors: up, down, strange, charm, bottom, and top. Due to a principle called color confinement, they are never observed in isolation, instead always forming groups of 2 or 3 to create particles known as mesons or baryons. For example, a proton is a composite of 2 up quarks and 1 down quark, whereas a neutron is made of 2 down quarks and 1 up quark. Their intricate dance is orchestrated by the strong interaction, which functions like an incredibly powerful magnet, binding everything together. When I reflect on quarks, it brings to mind my childhood fascination with dismantling toys to understand their internal mechanisms. Just imagine if we could directly observe and manipulate quarks. It would undoubtedly pave the way for revolutionary technologies, such as immensely powerful computers built on quantum principles. Researchers at facilities like CERN are already exploring this frontier by accelerating particles to velocities approaching the speed of light to investigate these interactions, with each new experiment uncovering fresh knowledge. Leptons, by contrast, represent a separate family of fundamental particles that includes the electron. There are 6 types in this group: the electron, muon, and tau, along with 3 kinds of neutrinos: the electron neutrino, muon neutrino, and tau neutrino. Unlike quarks, leptons do not experience the strong interaction, but are readily influenced by electromagnetism and the weak force. The electrons that orbit atomic nuclei are responsible for forming chemical bonds and enabling the flow of electricity, without which there would be no electric lights or internet. Neutrinos, however, are the genuine phantoms of the particle world. They interact so feebly with matter that they can traverse the entire Earth as if it were empty space, even as billions of them stream from the sun every second. I frequently wonder if neutrinos might harbor the secrets of dark matter, a revelation that could completely reshape our comprehension of the universe. For instance, experiments like the ice cube detector in Antarctica are capturing these elusive particles, and the thousands of events logged each year are helping us unravel the processes of stellar evolution. Take a moment to visualize these invisible currents flowing through the room you are in right now. It makes the realm of physics feel much more immediate and thrilling, doesn't it? Let us continue this captivating exploration with my thoughts on the Big Bang Theory, the foundational concept that allows us to comprehend how our immense universe originated. For me, it represents more than just a scientific model. It is a genuine portal to the past, offering a peek into those initial moments when everything came into being. Try to envision it. Roughly 13.8 billion years ago, all the matter, energy, and space we now observe were compressed into an unbelievably tiny, hot, and dense point. From this singularity, everything we know emerged, from the smallest particles to vast galactic clusters. My perspective on the Big Bang is that it describes the universe's initial state of extreme heat and density, from which it began to expand rapidly. This was not an explosion in the typical sense, where fragments are blasted into a void, but rather the stretching of space itself, as though the very fabric of reality were expanding. To grasp this better, imagine a rubber band with points drawn on it to represent distant star systems. As you stretch the band, the points all recede from one another uniformly, without any central point of detonation. This reminds me of how we witness growth in our own lives. A child doesn't expand from one spot, but develops harmoniously as a complete organism. Have you ever considered how such a simple parallel can illuminate a concept of such magnificent proportions? There is a wealth of evidence that supports this theory, and its persuasive power never ceases to amaze me. Consider, for instance, the cosmic microwave background radiation, also known as relic radiation, which is the thermal energy that permeates the universe. Its accidental discovery in the middle of the 20th century by two scientists has since established it as a cornerstone argument for the Big Bang. This radiation acts like an echo from the distant past, having cooled into the microwave frequency range over billions of years, due to the relentless expansion of the universe. Satellite studies of this radiation have revealed slight temperature variations, which, to me, are like the seeds in soil, the very seeds from which all galaxies and stars eventually formed. This data provides us with a snapshot of the universe in its infancy, helping us understand its composition at the very beginning of time. I often think that if we could travel back in time, we would be able to see this primordial glow with our own eyes. Isn't that a fascinating thought? Another compelling piece of evidence is the redshift observed in the light emanating from distant galaxies, which definitively indicates that the universe is still expanding. In the same way the sound of a receding siren drops in pitch, light waves stretch as the space between us and these objects increases, shifting them toward the red end of the spectrum. This monumental discovery, made by an astronomer in the early 20th century, completely transformed our perception of a static cosmos. Just try to imagine if the universe were motionless, how much more uninteresting our world would be. Current estimates place the universe's expansion rate at roughly 70 kilometers per second per megaparsec, a figure that injects a sense of constant motion into our cosmic view. Have you ever considered that everything we know is steadily moving apart? For me, this thought deepens my appreciation for our small world. This expansion model also provides a compelling explanation for the abundance of light elements like hydrogen, helium, and traces of lithium that we observe throughout the cosmos. These foundational elements were forged during nucleosynthesis within the first few minutes after the universe began, and their observed ratios align perfectly with theoretical predictions. I see it as a cosmic recipe where every ingredient is measured precisely, creating a balanced and harmonious universe. Current data suggests that ordinary matter is composed of approximately 74% hydrogen and 24% helium, with all other elements making up the remainder. This specific chemical makeup isn't a random occurrence. It serves as powerful confirmation of the theory. Naturally, even with these successes, some profound mysteries continue to capture my imagination. For instance, what are dark matter and dark energy? The substances believed to constitute the vast majority of the universe yet remain undetectable by our instruments. And what, if anything, preceded the start of everything? These are the questions that fuel the next wave of scientific investigation, and I am confident that future breakthroughs, potentially from advanced instruments like the James Webb Space Telescope, will begin to unravel these enigmas. Let's explore the timeline of events. In the instant following its creation, the universe was an incredibly hot and dense sea of pure energy, long before ordinary matter could exist. In place of atoms, there was a quark-gluon plasma, a soupy mix of fundamental particles where quarks, which build protons, and gluons, the carriers of the strong force, moved about freely in the intense heat. As the universe expanded and cooled within the first tiny fractions of a second, these particles started to bind together, forming the first protons and neutrons during what is known as the Hadron epoch. To me, it's a powerful example of structure emerging from absolute chaos. A few minutes into its existence, the process of nucleosynthesis commenced, with protons and neutrons fusing to create the nuclei of hydrogen, deuterium, helium, and lithium. As I mentioned, the resulting ratios, with helium comprising about a quarter of the total mass, are a perfect match for what we observe today. The universe, however, remained far too hot for stable atoms to form. It was only after hundreds of thousands of years, during an era called recombination, that electrons were finally captured by nuclei, forming the first neutral atoms and releasing a flood of light that we can still detect as the cosmic microwave background. Following this period, gravity began to assert its influence, pulling these primordial gases into vast clouds that eventually collapsed to ignite the first stars. It was within the fiery cores of these stars that heavier elements were forged, seeding the cosmos with the chemical diversity needed for life. I often think about how our planet, and indeed our very existence, is a direct consequence of this unbroken sequence of cosmic events, linking us back to the very beginning. Our confidence in this model is reinforced by key evidence, such as the discovery of the cosmic microwave background in the 1960s, and the formulation of the law of expansion back in the 1920s. This relic radiation reveals minute temperature variations, mere thousandths of a degree, that acted as the seeds for galaxy formation. Meanwhile, the fact of expansion logically leads to the conclusion that everything was once much hotter and more compact. The specific mix of light elements further corroborates early nucleosynthesis, and the universe's large-scale structure of galactic filaments and voids grew directly from those initial tiny imbalances. Let's now shift our focus to quantum fluctuations, a fascinating phenomenon where microscopic events have cosmic-scale consequences. Heisenberg's uncertainty principle states that you can never know both the exact position and momentum of a particle. A fundamental level of uncertainty is always present. This principle allows for fleeting bursts of energy in otherwise empty space, where virtual particles and their antiparticles spontaneously emerge and then vanish. While we cannot observe them directly, their impact is real and has been experimentally verified. For example, through the subtle shifts they cause in the orbital paths of electrons. Within the framework of the Big Bang, it's theorized that these very fluctuations served as the primordial seeds for the density variations that eventually grew into galaxies. Have you ever paused to contemplate how this fundamental quantum uncertainty has sculpted the large-scale universe you see today? It introduces a fascinating layer to science, encouraging us to think about the hidden mechanics that govern reality. I am convinced that a deeper understanding of this connection is crucial for future discoveries. I've always been convinced that quantum fluctuations are far more than a mere curiosity of physics. They are the very bedrock of the cosmos we inhabit. Consider that in the first moments after the Big Bang, the universe underwent a period of cosmic inflation, an astonishingly rapid and massive expansion. During this event, tiny quantum-level fluctuations were stretched to immense astronomical scales, establishing the initial variations in the density of matter. Over billions of years, gravity amplified these slight irregularities, shaping them into the vast galaxies and galaxy clusters we observe. We can still see the fossilized evidence of this process, imprinted on the cosmic microwave background, giving us a window into the universe's quantum origins and the delicate balance that allowed for our own existence. At the very foundation of these fluctuations is Heisenberg's uncertainty principle, which posits that you cannot simultaneously measure certain pairs of a particle's properties, like its position and its velocity, with perfect precision. Because of this fundamental limit, what you might consider an empty vacuum is in fact a dynamic environment, brimming with constant activity. Here, virtual particles and their corresponding antiparticles continuously spring into existence and vanish, effectively borrowing energy from space for a fleeting moment before they annihilate each other and restore the balance. Although you can't observe these virtual particles directly, their impact on the universe is immense. In specific circumstances, these quantum fluctuations can even give rise to real particles. Consider, for instance, the region near the event horizon of a black hole. Stephen Hawking theorized that pairs of particles and antiparticles can be pulled apart there. One partner is captured by the black hole's gravity, while the other is flung out into space, becoming a real, observable particle. This process causes the black hole to slowly lose mass and evaporate over vast timescales, which is a bit like taking out a loan and, instead of paying it back, using it to create something entirely new and real. I find this concept truly inspiring, as it demonstrates how something substantial can emerge from what appears to be nothing. And it makes me wonder just how many similar processes are unfolding around us, unnoticed. Another compelling illustration of this is the inflationary period of the early universe. According to this theory, the cosmos expanded at a breathtaking rate, and the quantum fluctuations present at that time were stretched to enormous macroscopic scales. These slight variations in density then served as the gravitational seeds for everything you now see, from individual star systems to massive clusters of galaxies. The virtual particles were essentially frozen into reality, contributing matter to the cosmic mixture. To make that concept a little clearer, you can think of it like dough rising. The tiny air bubbles within it expand as the bread bakes, creating its final porous structure. In much the same way, these initial fluctuations were baked into the fabric of the cosmos. Some scientific estimates suggest that as much as 90% of all the visible matter in the universe today may have originated from this very process. This highlights the profound link between the infinitesimally small quantum world and the grand scale of cosmology, effectively blurring the distinction between emptiness and substance. Have you ever considered how these microscopic events ultimately led to you standing on Earth, gazing up at the stars? As you delve deeper into this subject, it's impossible to overlook the critical role that energy plays in the creation of particles, acting as a bridge between transient fluctuations and solid reality. Energy serves as the catalyst that transforms the potential hidden within these fluctuations into actual matter. You might recall Albert Einstein's famous equation, which states that energy is equal to mass multiplied by the speed of light squared, revealing that energy and mass are fundamentally interchangeable. The vacuum, seemingly void, is actually seething with these fluctuations, generating momentary bursts of energy from which particle-antiparticle pairs can form. Under normal conditions, these pairs quickly annihilate each other. But in extreme environments, like the very early universe, they can become stable and persist. I think this is comparable to how, in our daily lives, we transform energy like electricity into light or heat. Only in the cosmos, this process forges entire worlds. In the initial moments following the Big Bang, the universe was a hot, dense soup of pure energy. As this cosmic soup expanded and cooled, energy began to congeal into particles, following this same basic principle. The universe progressed through distinct phases, from the quark epoch, where quarks and gluons moved freely, to the subsequent formation of protons and neutrons. Energy not only birthed these particles, but also governs their interactions. Look at the stars, for example. Within their cores, the energy released by nuclear fusion forges heavier elements, everything from carbon to iron, without which life as you know it couldn't exist. It's a cascading effect. Energy creates matter, and that matter, in turn, generates new forms of energy. I often relate this to gardening, where the sun's energy is converted into plant growth, building complex structures from simple seeds. Statistical data indicates that approximately 75% of the universe's mass is composed of hydrogen and helium that were created in those first few moments. Doesn't that make you contemplate the intricate interconnectedness of everything? Returning to Heisenberg's uncertainty principle, it's far more than just an abstract concept. It represents a fundamental haziness inherent to our world at the quantum level. Introduced by Werner Heisenberg in 1927, the principle establishes that it is impossible to know both a particle's exact position and its precise momentum at the same instant. This limitation isn't due to flawed instruments, but is an intrinsic property of reality itself. In a vacuum, this principle permits virtual particles to momentarily exist in violation of energy conservation, but only for an incredibly short time. While these pairs usually vanish, extreme conditions near a black hole or during cosmic inflation can make them real. Here's an analogy. Imagine you are trying to catch a butterfly in a dark room. The more accurately you pinpoint its location, the less you can know about its trajectory. This principle beautifully illustrates how uncertainty is a creative force in the cosmos. I personally feel this teaches us a degree of humility. In science, just as in life, absolute certainty is often an illusion, and it is this very lack of precision that leaves room for wonder and discovery. In the very first fractions of a second after the Big Bang, the universe was far too hot for ordinary particles to exist. Instead, there was a quark-gluon plasma, a state where quarks, the eventual building blocks of protons and neutrons, swam in a sea of gluons, which carry the strong nuclear force. As the universe cooled over microseconds, these quarks began to bind together, forming protons and neutrons in what is known as the hadron epoch, a pivotal stage in the development of complex matter. This was followed by the lepton epoch, a period lasting from 1 second to several minutes, where electrons and similar light particles were dominant. Although the cosmos was still too hot for atomic nuclei to form, this soon changed, leading to the era of primordial nucleosynthesis. During this time, protons and neutrons fused to create the nuclei of hydrogen, helium, and trace amounts of lithium and beryllium, laying the elemental groundwork for the future. However, complete atoms with orbiting electrons wouldn't appear until much later, after about 380,000 years, during an event called recombination. It was then that matter decoupled from radiation, leaving behind the cosmic microwave background, which serves as a snapshot of the infant universe. Have you ever tried to place yourself within that primordial soup? Doing so can help you grasp how deeply we are shaped by those ancient cosmic events. Let's delve into the separation of the fundamental forces, a process that resembles a symphony where order gradually arose from chaos. In the very beginning, extreme heat unified all these forces into one. But as the cosmos expanded and cooled, this perfect symmetry shattered. Gravity was the first to break away, just a fraction of a second after the Big Bang, establishing the framework for large-scale structures by pulling matter together to form stars and galaxies. Following gravity's lead, electromagnetism and the strong and weak nuclear forces also went their separate ways. This divergence is much like biological evolution, where complexity emerges from a simpler state. I often reflect on the fact that without this separation, we wouldn't have magnets, nuclear power, or even the simple ability to stand firmly on the Earth. It's an invitation to consider how these fundamental forces govern your own daily existence, from the orbital pull of planets to the electricity that powers a simple light bulb, reminding us that we are all participants in a grand cosmic ballet that started billions of years ago. Quantum fluctuations are far more than just a peculiar aspect of quantum physics. Many scientists believe they were the decisive factor in shaping our universe. This story begins during the inflationary phase, an unimaginably brief period of hyperexpansion that took place a split second after the Big Bang. During that instant, minuscule quantum ripples were stretched to colossal proportions, amplifying slight variations in the density of matter. It was from these initial seeds that the vast structures we see today, galaxies, galaxy clusters, and immense superclusters, ultimately grew. Traces of this ancient past are permanently imprinted on the cosmic microwave background, the relic radiation that acts as a window into the quantum origins of everything. It's a staggering thought that what appears to be empty space is, in reality, teeming with an invisible energy that actively sculpts the cosmos. All of this is underpinned by the renowned uncertainty principle, first formulated by Heisenberg. It dictates that you cannot simultaneously know certain pairs of a particle's properties, like its precise position and its exact velocity, with perfect accuracy. Because of this fundamental limitation, even a perfect vacuum is never truly void. Instead, it seethes with a constant flux of virtual particles that wink into and out of existence. They are called virtual because they cannot be observed directly, as they borrow energy for an infinitesimal moment before annihilating each other and repaying their energetic debt. Yet, under specific conditions, these fleeting particles can become entirely real. For instance, consider the region around a black hole, where the effect predicted by Stephen Hawking occurs. Near the event horizon, quantum fluctuations can spawn a particle-antiparticle pair. If one particle falls into the black hole while its partner escapes, the escaping particle becomes real. This process results in the black hole slowly losing mass, almost as if it were evaporating over time. I've always found this concept astonishing. The idea that tangible reality can spring from apparent emptiness, like a spark of life emerging from nothing. Have you ever considered how this transforms our perception of a void? Perhaps our everyday lives are similarly surrounded by such unseen formative processes. The inflationary epoch of the early universe offers another compelling example. According to this theory, the cosmos underwent a period of breathtakingly rapid expansion just after its birth. During this time, quantum fluctuations were stretched out, evolving into significant inhomogeneities on a massive scale. These density waves laid the groundwork for all cosmic structures, from singular galaxies to the vast cosmic web that connects them. Virtual particles could also become frozen into reality, contributing to the overall matter in the universe, which illustrates the profound connection between quantum mechanics and cosmology. The most minuscule effects ultimately govern the grandest scales. To grasp this better, you can draw an analogy with the ocean. Its surface might look calm, but deep beneath, powerful currents are churning, capable of creating waves and even massive storms. In the same way, the quantum foam provides the very foundation for everything we can see. As a personal reflection, when I contemplate this, our universe seems like a colossal canvas where seemingly random brushstrokes coalesce into a masterpiece. And the statistics bear this out. Observations of the cosmic microwave background from satellites like Planck reveal temperature variations with an amplitude of only 1/1/10,000th of a degree. Yet it was these incredibly subtle fluctuations that gave rise to all the galaxies. This mechanism, where particles are born from fluctuations, underscores how deeply the quantum world is woven into the fabric of cosmic evolution, blurring the boundary between emptiness and reality, between nothingness and existence. Exploring further, the role of energy is impossible to ignore, as it acts as the very bridge between fleeting fluctuations and solid matter. Energy is the catalyst that converts potentiality into actual particles, a process governed by Albert Einstein's famous equation, where energy is equal to mass times the speed of light squared. This reveals that energy and mass are simply two different manifestations of the same thing. The vacuum, though seemingly empty, is effectively a boiling cauldron of quantum fluctuations, where energy levels continuously rise and fall, allowing particle-antiparticle pairs to emerge. While these pairs usually vanish instantly, returning their borrowed energy, they could persist under the extreme conditions of the early universe, which was a hot, dense soup of energy. As the cosmos cooled, this raw energy solidified into particles. I often compare it to making a stew. Initially, everything is a chaotic liquid, but as it cools, solid chunks, protons and neutrons begin to form. Cosmological data indicates that the temperature then was in the trillions of degrees, creating the perfect environment for these transformations. In those very first moments, the universe was simply too hot for any stable particles to exist at all. In the very beginning, The universe was nothing but quark-gluon plasma, a state where the future components of protons and neutrons, the quarks, drifted freely in a sea of gluons, which are the carriers of the strong interaction. As the cosmos expanded and its temperature dropped, within mere microseconds, these quarks began to coalesce into protons and neutrons. This marked the beginning of the Hadron Epoch, a pivotal transition toward the formation of complex matter. Let's consider the fundamental forces. In the earliest moments, gravity, electromagnetism, and the strong and weak nuclear forces were all indistinguishable, merged into a single entity. As the universe cooled, this perfect symmetry shattered, and the forces began to separate. Gravity was the very first to break away, just an infinitesimal fraction of a second into existence, which established the conditions necessary for creating large-scale structures. You can think of it like an egg cracking. From a unified whole, distinct parts with unique functions emerge, and without this separation, neither stars nor planets could have formed. For me, this serves as a powerful illustration of unity, showing how everything in the cosmos, from the tiniest fluctuations to entire galaxies, is interconnected. At the dawn of our universe, all of nature's fundamental forces, which direct everything from electromagnetism to the strong nuclear bonds and weak decay processes, were harmoniously united. This unified state held until the cosmos cooled to a critical temperature, triggering the first momentous split. The strong force, responsible for binding quarks into protons and neutrons and holding atomic nuclei together, broke away from the unified electro-weak force. You might visualize this as a great ocean parting into separate rivers. Each follows its own course, yet all originate from the same source. This event happened with incredible speed during the inflationary epoch, a period of astonishingly rapid expansion just a fraction of a second after the Big Bang, and it laid the foundation for the elementary particles that would eventually constitute the matter we see today. Following this, the still combined electro-weak force governed the superheated cauldron of energy, but it too was destined to split as the universe continued to cool. At approximately 10 to the power of minus 12 seconds after the Big Bang, this symmetry also broke, causing the force to divide into the familiar electromagnetic force, which is carried by photons, and the weak force, which drives radioactivity and stellar synthesis. I often compare this to a child's development, where specialized abilities arise from an undifferentiated state, enabling more complex growth. This event finalized the formation of the four fundamental forces we know, setting the stage for further cooling and the creation of intricate structures. Have you ever considered how these ancient events dictate our present reality? It was precisely these separations that transformed primordial chaos into an ordered system where matter could assemble, making everything you observe possible. Now, let's take a closer look at the electro-weak epoch, the crucial phase that immediately followed the universe's birth. This was the period, lasting from 10 to the power of minus 12 to 10 to the power of minus 6 seconds, when the electromagnetic and weak forces remained fused. The universe at this time was a searing hot soup of particles, a dense plasma teeming with quarks, leptons, their antiparticles, and the bosons that carried the single, unified force. As this cosmic fluid expanded and its temperature fell, the critical moment of symmetry breaking occurred. It was as if a hidden barrier fell, allowing the forces to diverge into the electromagnetic force, mediated by photons, and the weak force, associated with W and Z bosons. This separation is far more than a technical detail. It's the very bedrock of all particle physics. The Higgs mechanism, linked to the field that imparts mass to particles, played a central role here. It was through interaction with this field that particles acquired their weight, an event that directly caused the forces to split. The discovery of the Higgs boson in 2012 was a monumental scientific victory, validating our theoretical models. I personally find it to be a stunning example of how theory can accurately predict the fabric of reality, much like finding the final piece that makes a complex puzzle snap into place. This confirmation not only reinforced the Standard Model, but also encourages us to contemplate the unity of nature and ask whether similar mechanisms might be at play on entirely different scales. Let's now turn to quarks, the elementary constituents of matter that are governed by the strong interaction. This particular force, one of the four fundamental ones, is immensely powerful, but is effective only over microscopic distances. It acts like an unbreakable glue, binding quarks together in groups of three to create baryons, such as protons, which consist of two up quarks and one down quark, and neutrons, which are made of two down quarks and one up quark. The resulting charge of the particle is determined by this specific combination, making protons positive and neutrons neutral. This entire process of formation began once the universe had cooled sufficiently for quarks, which had been moving freely in the quark-gluon plasma, to start clustering together. First, pairs of quarks and antiquarks emerged, followed by triplets that would evolve into the stable particles we know today. Without this confinement of quarks within protons and neutrons, there would be no atoms, no stars, and certainly no us. This incredible transition from a state of freedom to one of intricate structure always reminds me of how a beautiful symphony arises from a collection of scattered notes. The fact that approximately 75% of the universe's matter is hydrogen, which is built from these very protons, highlights the immense importance of that era. This period of hadronization, or the formation of hadrons from quarks, paved the way for the next great chapter in cosmic history, nucleosynthesis, when the first atomic nuclei started to form as the universe continued to expand and cool. Roughly 3 minutes after the initial cosmic event, the strong nuclear force triumphed over electromagnetic repulsion, enabling protons and neutrons to fuse. This process gave rise to the first atomic nuclei: hydrogen, helium, and trace amounts of deuterium, tritium, lithium, and beryllium. This era of primordial nucleosynthesis is pivotal, as it established the elemental composition of the universe, about 75% hydrogen and 25% helium, a ratio that aligns with current observations and validates the Big Bang theory. I often consider how, without this step, the cosmos would have lacked the chemical complexity essential for life. A slightly higher temperature back then would have meant no planets, and therefore, no you and me. Our cosmic history then advances to the period of the first atoms, approximately 380,000 years later. By this time, the universe had cooled sufficiently for electrons to be captured by atomic nuclei, forming stable, neutral atoms in a process known as recombination. Before this, the cosmos was an opaque plasma, where free-floating electrons scattered light, much like a dense fog. As the universe expanded and cooled, photons lost energy, allowing electrons to bind to nuclei, which suddenly rendered the cosmos transparent. The photons that escaped at that very instant now constitute the cosmic microwave background, a faint afterglow of the Big Bang that we can still detect today. With the formation of these first atoms, The cosmic dark ages came to an end, and gravity could begin its work of gathering matter into the first stars and galaxies. Nuclear fusion ignited within these stellar cores, forging heavier elements and enriching the cosmos with a greater diversity of materials. The universe, after recombination, was composed almost exclusively of hydrogen and helium, but the creation of a more intricate world demanded the heavier elements that could only be produced in this next stage. The stars, in essence, became the cosmic forges that transformed the simplest elements into the building blocks of everything that would follow. While primordial nucleosynthesis provided the light elements, the creation of all other elements depended on stars. Within their fiery hearts, hydrogen atoms fuse to become helium, which in turn fuses into carbon. And this chain reaction continues, creating progressively heavier elements up to iron in the most massive stars. Producing elements heavier than iron, however, requires the cataclysmic conditions of a supernova. During these stellar explosions, neutrons are captured in rapid succession, generating the heaviest elements, which are then ejected across the galaxy, seeding the interstellar medium with the raw materials for new generations of stars and planets. Let me offer a personal thought. As you learn about these processes, I encourage you to contemplate your own place within this grand cosmic narrative. Every atom in your body was forged in the core of a distant, long-dead star, a concept that personally makes the study of science profoundly inspiring. Have you ever paused to truly imagine the journey of the carbon that makes up your very being? That kind of reflection connects us directly to the universe's incredible history. Particle accelerators are monumental feats of engineering designed to take charged particles, like protons and electrons, and propel them to nearly the speed of light. These particles are then smashed into one another or into stationary targets, which recreates the extreme energies and temperatures that existed moments after the Big Bang. This allows scientists to investigate the fundamental constituents of matter and the forces that govern their interactions. It's a method akin to dismantling a complex machine to understand its innermost workings and principles. To achieve this, accelerators employ powerful electric fields to boost the particles' speed and immense magnetic fields to guide their paths. This control is applied whether the particles are traveling in a straight line, as in linear accelerators or linacs, or in a circular path, as in synchrotrons. When these high-velocity particles collide, they unleash a shower of new, often exotic particles, giving us a window into the physics of the primordial universe. I sometimes find myself wondering what it would be like to witness that era firsthand. In a very real sense, these machines serve as our telescopes into time itself. These incredible machines have applications that extend far beyond fundamental research. The Large Hadron Collider, or LHC, located at CERN near Geneva, is the world's most powerful accelerator, designed to probe mysteries like the Higgs boson and the nature of dark matter. Yet, the technology also drives innovation elsewhere. In medicine, accelerators are used to generate particle beams for treating cancer, and to create radioactive isotopes for diagnostic imaging. In industry, they are used to modify materials and fabricate microchips, while in archaeology, they can scan priceless artifacts without causing any damage, providing a kind of high-tech vision into the past. The design and construction of these accelerators represent a summit of human ingenuity, requiring a synthesis of technologies like superconducting magnets, ultra-high vacuum systems, and sophisticated particle detectors. More than just instruments for discovery, They are powerful engines of innovation that continually advance the frontiers of technology. I often think about the vast number of everyday devices and conveniences that owe their existence to the technological breakthroughs first developed for this kind of high-level scientific research. Ultimately, accelerators have been indispensable in deepening our comprehension of the universe's fundamental laws, sparking breakthroughs that have reshaped modern physics. By enabling us to collide particles at tremendous energies, they have provided a direct view into the core of matter, unveiling the subatomic particles and forces that construct our reality. One of the most significant triumphs came in 2012, when experiments at the Large Hadron Collider confirmed the existence of the Higgs boson, a particle that perfectly completed the theoretical framework known as the Standard Model. The Higgs boson is the particle that provides an explanation for why other particles possess mass, and its identification marked a monumental achievement, earning François Englert and Peter Higgs the Nobel Prize in 2013. Just try to picture the emotions of those scientists when the discovery was announced. It was like discovering the final, crucial piece to a puzzle that had perplexed the scientific community for generations. This breakthrough also served to reinforce the theory of electroweak unification, advancing us closer to a comprehensive theory of forces. Particle accelerators were also instrumental in demonstrating the existence of quarks, which are the fundamental components of protons and neutrons. Between the late 1960s and early 1970s, experiments conducted at the Stanford Linear Accelerator delivered the first tangible proof, validating the theories put forth by Murray Gell-Mann and George Zweig. This discovery fundamentally altered our conception of matter's structure, revealing a universe far more intricate than we had previously imagined. Then there is the subject of antimatter. Accelerators have given us the capability to produce and examine its constituent particles, which are essentially mirror images of ordinary matter but with reversed electrical charges. At facilities like CERN and others, researchers are able to trap anti-hydrogen to probe the fundamental symmetries of the cosmos. A profound question remains. Why does matter dominate over antimatter when the Big Bang theory posits they should have been created in equal amounts? Solving this enigma could completely reshape our knowledge of the universe's origins. Beyond fundamental physics, accelerators have spurred progress in oncology with the development of beam therapy, and even originated the World Wide Web, created as a system for scientists to share data. When you consider the broader impact, just think of the number of lives saved by these innovations. Data indicates that particle beam therapy is used to treat millions of cancer patients each year, enabling a more targeted and successful fight against the disease. Let's turn to how these experiments actually validate theoretical forecasts. In the world of particle physics, theory and experimentation are intrinsically linked. Theorists construct mathematical frameworks that predict particle behaviors or the potential existence of undiscovered particles. Experimental physicists then employ accelerators to accelerate and collide these particles, meticulously documenting the outcomes with advanced detectors. The subsequent data analysis is a scientific discipline in itself, involving complex algorithms and rigorous checks, with reproducibility being the ultimate goal. When multiple independent teams across the globe observe the identical phenomenon, it signifies more than mere chance and builds confidence in the result, which is a foundational principle of all science. The Standard Model serves as the foundational theory of contemporary physics, outlining three of the universe's primary forces: the electromagnetic, weak, and strong interactions. It systematically categorizes every known elementary particle and offers our most accurate description of how they interact. This model was developed over many decades, starting in the mid-20th century, and successfully merges quantum mechanics with special relativity into what is known as quantum field theory. Within this framework, particles are sorted into fermions, like quarks and leptons, which constitute matter, and bosons, which are the carriers of force, such as photons for electromagnetism and gluons for the strong nuclear force. The crowning achievement of the model was its prediction of the Higgs boson, which was finally confirmed in 2012. This particle is responsible for imparting mass via the Higgs field, an unseen energetic web that lends substance to everything. However, the standard model is incomplete, as it notably omits gravity, as formulated by Einstein. It also fails to provide any explanation for dark matter or dark energy, which together are estimated to comprise 95% of the entire cosmos. For all its remarkable successes, the Standard Model contains significant gaps, such as why particles have their specific masses, underscoring the fact that our grasp of the universe is still partial. It is precisely these limitations that propel scientists to explore new frontiers of knowledge. Its most glaring omission is gravity, the force that commands the cosmos on immense scales, from the orbits of planets to the structure of galaxies. The model, however, is founded on quantum mechanics, into which gravity simply does not integrate, creating an enduring puzzle of how to unite the macroscopic and microscopic realms. Moreover, the model remains silent on the nature of dark matter and dark energy, which observations suggest are the dominant components of the universe. I find myself wondering if dark matter is composed of entirely new particles, just waiting for us to find them. This thought fuels the hope that the next wave of particle accelerators will finally solve these profound riddles. Just imagine the transformation our world would undergo if we could master gravity on a quantum scale. What are your thoughts on these great unknowns? It might be worth reflecting on how such discoveries could impact your own life, as science is not confined to labs, but shapes the shared future we are all moving toward. What secrets are concealed in the frigid quiet at the far reaches of our solar system? In that distant realm, where sunlight fades to a faint glimmer in the vast emptiness of space, humanity has looked to the heavens for centuries, compelled by an unquenchable desire to understand. It is only in recent times, however, that our robotic explorers have made contact with these enigmatic worlds, completely transforming our perception of our cosmic neighborhood. The narrative we believed was complete has been revealed as merely the introduction to a much grander story, filled with active terrains and geological marvels in places we assumed were defined by perpetual cold and quiet. Even with its immense separation from the sun and the absence of strong tidal interactions to produce internal warmth, Pluto showed evidence of continuous surface regeneration. This discovery prompts fresh inquiries into the internal mechanisms that could be active in other remote bodies within its home, the Kuiper Belt. The mission also rekindled the controversy over what defines a planet, as Pluto's surface is in constant motion, shaped by geological and atmospheric processes that defy expectations for a dwarf world. While the debate persists, one certainty has emerged. Pluto is not a lifeless, frozen rock, but a vibrant world of frigid enigmas and constant transformation. Even with its immense separation from the sun and the absence of strong tidal interactions to produce internal warmth, Pluto showed evidence of continuous surface regeneration. This discovery prompts fresh inquiries into the internal mechanisms that could be active in other remote bodies within its home, the Kuiper Belt. The mission also rekindled the controversy over what defines a planet. As Pluto's surface is in constant motion, shaped by geological and atmospheric processes that defy expectations for a dwarf world. While the debate persists, one certainty has emerged. Pluto is not a lifeless, frozen rock, but a vibrant world of frigid enigmas and constant transformation. Sputnik Planitia offers one of the most compelling signs of Pluto's activity, presenting a surface etched with distinctive polygonal shapes. Far below this plane, sluggish convective currents circulate material, pushing it up in some locations and drawing it down in others, which constantly renews the landscape and wipes away ancient impact craters. This dynamic is reminiscent of the molten rock circulation beneath our own planet's crust. But on Pluto, the medium is frozen nitrogen, not liquid magma. While Earth's geological forces are fueled by heat from radioactive decay deep within its core, Pluto is too small and distant from the Sun to possess such an internal engine. Instead, researchers theorize that the gradual freezing of a potential subterranean ocean powers these surface transformations. Further evidence of Pluto's dynamic nature can be found in its glaciers, which seem to creep across the terrain. Unlike the water ice glaciers on Earth, these are made of frozen nitrogen that slowly migrates, carrying material from higher elevations down to Sputnik Planitia. Certain areas display signs of ancient, now stationary glacial flows, whereas other evidence points to this being a currently active process. The New Horizons probe also identified a multitude of pits and depressions dotting Pluto's surface, many of which are thought to be caused by ice sublimation, the direct transformation of a solid into a gas. Exposed to sunlight, Pluto's nitrogen and methane ice can turn to vapor, a process that steadily reshapes the landscape over immense timescales. Pluto possesses an exceptionally tenuous atmosphere, composed primarily of nitrogen, with small amounts of methane and carbon monoxide. This thin atmospheric layer experiences dramatic fluctuations as Pluto traces its long oval-shaped path around the Sun. During its closest approach, surface ices are warmed just enough to release gases, thickening the atmosphere, while at its farthest point, these gases freeze and fall back to the surface as fresh, icy layers. This atmospheric breathing is thought to be the primary driver of the seasonal transformations seen on the dwarf planet, which unfold over its full 248-year orbital period. Among the most enigmatic features on Pluto are the dark, reddish-brown patches visible in specific areas, such as the equatorial dune fields and the expansive dock terrain named Cthulhu Macula. Scientists believe these discolorations are caused by complex organic molecules known as tholins. These compounds are created when ultraviolet radiation from the Sun strikes methane in Pluto's atmosphere, and over eons they drift down to coat the surface. The way these dark materials are spread across the landscape indicates that Pluto's surface chemistry is in a continuous state of flux, shaped by both atmospheric and geological forces. The findings from the New Horizons mission imply that Pluto is far from an anomaly. Many other bodies within the Kuiper Belt could be similarly active and evolving in ways we are only beginning to grasp. Future explorations planned for 2024 into this remote part of the solar system may uncover more startling revelations, continuing to dismantle the notion that small, icy worlds are simply inert relics. Situated beyond Pluto is the immense and enigmatic expanse of the Kuiper Belt, a domain filled with frozen objects and primordial leftovers from the dawn of planetary formation. It wasn't until the end of the 20th century that observational technology confirmed its existence, fundamentally altering our view of the outer solar system. This region is populated by innumerable icy bodies, ranging from just a few kilometers in diameter to some that are comparable in size to Pluto itself. Known as Kuiper Belt objects, or KBOs, they occupy a broad, disc-shaped zone that stretches billions of kilometers into space. In contrast to planets, which have cleared their orbital paths, these KBOs are dispersed widely and follow diverse trajectories, suggesting a history of gravitational disturbances from Neptune and the other gas giants. Researchers consider these objects invaluable, as they are believed to be composed of the same pristine materials that came together to form the planets over 4 billion years ago, offering a direct window into the solar system's origins. Perhaps the most astonishing discovery of the New Horizons mission occurred after it passed Pluto and ventured further into the Kuiper Belt, where it encountered a small, primeval object called Arakoth. In stark contrast to Pluto's intricate and active surface, Arakoth seems to be a time capsule, preserved almost perfectly since the solar system's birth. Its smooth reddish exterior is coated in frozen methane, indicating it has been in a deep freeze for billions of years. Arakoth's peculiar shape, resembling two gently merged lobes, points to a calm formation process in the tranquil early Kuiper Belt. Unlike the violent impacts that shaped many asteroids closer to the Sun, this finding has offered profound insights into the initial formation of planetesimals, the fundamental building blocks of planets. You'll find that many Kuiper Belt objects, or KBOs, travel along peculiar paths, with some showing clear evidence of Neptune's gravitational influence from the distant past. Then you have outliers, like Sedna, which follows a tremendously stretched-out orbit that takes it well beyond the Kuiper Belt's accepted edge. This has led many to question if there are other, unseen planets in the far reaches of our solar system, with some researchers postulating that a massive, yet-to-be-found world, nicknamed Planet 9, could be shaping the trajectories of these remote objects from its hiding place far beyond Pluto. I should point out that the Kuiper Belt is also populated by other dwarf planets that are quite similar to Pluto. Take Eris, for example. It's one of the most massive objects discovered in the region, and, since its identification in 2005, we've learned it's almost identical in size to Pluto. The discovery of Eris was instrumental in Pluto's reclassification, as it proved to astronomers that Pluto was not a lone wanderer, but simply one of several large bodies in this distant realm. Eris itself has an exceptionally reflective surface, coated in frozen methane and nitrogen, and travels on an orbital path that carries it significantly farther from the Sun than Pluto ever gets. And there are other worlds out there for you to consider, like the dwarf planet Makemake, which is a bit smaller than Pluto and has a surface blanketed in methane ice, though it is missing a substantial atmosphere. Some bodies in the Kuiper Belt exhibit truly strange behaviors. For instance, you have Haumea, a large object that spins at an astonishing rate, finishing a full rotation in under 4 hours. This rapid spin has distorted Haumea into a stretched, oblong form, distinguishing it as one of the most peculiar large bodies known in the solar system. Furthermore, Haumea is encircled by its own ring of debris, a feature that makes it the only KBO we know of with such a structure. This finding leads me to believe that collisions between objects in the Kuiper Belt were likely a frequent occurrence in the solar system's early history, flinging out debris that would later coalesce into the rings or moons we see today. Many of these bodies are composed of a mix of water ice, methane, and various other frozen compounds that have remained essentially pristine since the solar system first formed. By examining their orbits and surfaces, scientists like myself can piece together a history of how the giant planets migrated and disturbed the surrounding material billions of years ago, with some models indicating that Neptune once drifted outward, scattering KBOs into their current positions and sculpting the very architecture of the region. Because the Kuiper Belt stretches so far out, and its inhabitants are often too dim and small to be seen from Earth, observing it is an immense challenge, which is why the New Horizons mission gave us such a precious look into this remote part of the solar system. To learn more, however, you must understand that we will need dedicated future missions. Some proposals involve sending a new probe even deeper into the belt to analyze the makeup of several objects directly. Alternatively, others place their hopes in powerful new observatories, like the James Webb Space Telescope and its successors, which could potentially spot more KBOs and help us better define their characteristics from afar. As you venture conceptually beyond the Kuiper Belt, the solar system gives way to an even more enigmatic domain, called the Oort cloud. Whereas the Kuiper Belt is a relatively flat, disc-shaped region of space, I can tell you the Oort cloud is theorized to be a gigantic spherical shell of icy bodies enveloping our entire solar system. These objects are far too remote to be observed directly. We only infer their existence from the long-period comets that sometimes journey into the inner solar system. It's possible that some of these comets actually began their lives in the Kuiper Belt, before gravitational pushes from Neptune or other planets ejected them into these vast, distant orbits. The remarkable legacy of the Voyager probes represents a true leap across the final frontier of our solar system. What began as a bold initiative to survey the outer planets grew into a mission of much grander scale, a voyage into interstellar space itself. Launched in 1977, Voyager 1 and Voyager 2 were timed to exploit a planetary alignment so rare it happens just once every 176 years. This celestial arrangement enabled them to use gravity assists, slingshotting from one planet to the next, which dramatically boosted their velocity and prolonged their functional lives, turning a planned tour of Jupiter and Saturn into an escape from the Sun's dominion. Voyager 1 became the first human-made object to enter interstellar space, definitively crossing the edge of the heliosphere in 2012. You should think of the heliosphere as a massive bubble formed by the solar wind's charged particles and magnetic fields. Its boundary is where the Sun's influence yields to the forces of the wider galaxy. Voyager 2 made the same crossing in 2018, offering another crucial set of data for comprehending this boundary. Both probes continue to transmit data on cosmic rays, magnetic fields, and particle density, giving us our first direct measurements of the environment that lies beyond our solar system. Before they embarked on this interstellar journey, the Voyager spacecraft provided you and all of humanity with our first detailed look at the gas giants and their diverse moons. During its 1979 encounter with Jupiter, Voyager 1 captured stunning images of the planet's chaotic atmosphere, including its Great Red Spot, a storm that has been raging for centuries. The probe also made the groundbreaking discovery that Jupiter's moon Io is volcanically active. This entirely unexpected observation revolutionized our models of how moons can generate internal heat through the immense tidal forces exerted by their parent planets. And Voyager 2 followed a unique trajectory that allowed it to visit all four of the outer planets: Jupiter, Saturn, Uranus, and Neptune. When you look at what Voyager accomplished at Saturn, you see it sent back incredible images of the planet's elaborate ring system. These pictures demonstrated how the rings consist of countless distinct particles that weave together into complex and beautiful patterns. The probe also investigated Titan, where a thick, hazy atmosphere blocked the view of the surface, suggesting that an active world was concealed beneath the dense cloud cover. Uranus remained largely a puzzle until Voyager 2's visit in 1986. In contrast to other gas giants with their vibrant, swirling atmospheres, Uranus appeared to be an almost completely featureless blue-green sphere. However, the spacecraft uncovered that the planet's magnetic field is tilted at a very sharp angle, which may be the result of a massive collision in its distant past. Additionally, Voyager 2 detected signs of rings orbiting Uranus, which are much thinner and more difficult to see than Saturn's. The probe's flyby of Neptune in 1989 turned out to be equally revelatory. You'll find that Neptune's atmosphere is significantly more active than that of Uranus, hosting the most extreme winds ever documented in the solar system. Voyager 2 also spotted the Great Dark Spot, a colossal storm reminiscent of Jupiter's Great Red Spot, although this feature had disappeared when the Hubble Space Telescope observed the planet in later years. I believe the most defining moment of the Voyager mission happened in 1990, when Voyager 1 aimed its camera back at Earth to capture the renowned pale blue dot photograph. From a staggering distance of 3.7 billion miles, our world was just a tiny fleck, almost lost in the sheer scale of space. This single image, elevated by the reflections of astronomer Carl Sagan, evolved into a powerful reminder of humanity's fragile place within the universe. As the Voyager probes moved beyond the planets, their journey continued, but with a new purpose, as interstellar explorers. Their instruments, which you'll remember were built for studying planets, were cleverly repurposed to analyze the boundary of the heliosphere and the crossing into interstellar space. The heliopause, the frontier where solar wind yields to the interstellar medium, had been a theoretical idea for a long time, but it had never been directly measured. When Voyager 1 crossed this boundary, scientists received confirmation that the density of particles around it had jumped, signaling its exit from the Sun's direct influence. 6 years later, Voyager 2 traversed the heliopause along a different trajectory. Its data confirmed that the edge of our solar system is not a static line. It actually flexes and shifts with solar activity, causing the heliosphere to expand and contract, much like a lung. The region beyond the heliosphere is far from empty. Instead, it's permeated by a delicate mixture of gas and dust called the interstellar medium. This substance is composed of the remnants of ancient stars that existed and perished long before our own solar system formed. The Voyager data provided the first direct measurements of this medium, revealing that it is denser than had been assumed, and that charged particles there behave differently than they do inside the heliosphere. One of the unexpected findings from the Voyager's journey was the detection of pressure waves moving through interstellar space. These waves are generated when the Sun has coronal mass ejections, which are powerful bursts of energy. Although they start near the Sun, these disturbances travel outward until they finally collide with the interstellar medium, and the probe's instruments were able to record them as they passed by. The area immediately past the heliopause also revealed itself to be more intricate than anyone had predicted. Rather than a gentle transition, Voyager discovered a chaotic zone where particles from our Sun and from interstellar space intermingle. By studying this region, which contains the fundamental materials for new stars and planets, we can gain a better understanding of how planetary systems come into being from the debris of older stars. As the Voyager spacecraft ventured deeper into space, their sensors are detecting fewer particles originating from our Sun and a greater number from interstellar sources. These ongoing measurements are invaluable for helping scientists improve their models of how the heliosphere as a whole interacts with the rest of the galaxy. Eventually, the probes will reach a point where the Sun's influence is nearly zero, offering an unprecedentedly clear view of the interstellar medium. Scientists now theorize that the heliosphere's very shape is influenced by forces external to our solar system. It's believed the Sun is currently passing through a denser patch of interstellar space, which could be altering the heliosphere's size, and it's to shield us from cosmic radiation. The Voyager's data will be crucial in determining if this galactic neighborhood has affected Earth's climate in the past. One fundamental question is still unanswered. Just how far does the Sun's dominion truly reach? Even though the Voyager spacecraft have passed beyond the heliosphere, the Sun's gravity continues to hold sway over the distant comets in the Oort cloud. It will be many thousands of years before the probes finally arrive at the true edge of our solar system, the point where the Sun's gravitational pull fades away completely. Cosmic rays represent some of the most energetic particles known in the universe, hurtling through the cosmos at velocities approaching the speed of light. Their origins are traced to a variety of powerful cosmic events, from the explosive remnants of massive dying stars known as supernovae, to even more enigmatic phenomena like black holes and the collision of neutron stars. These particles, along with magnetic currents, are invaluable for helping us navigate uncharted cosmic territories. For many decades, the nature of these particles was shrouded in mystery, as you could only detect them indirectly through the aftermath of their collisions with Earth's atmosphere. However, as the Voyager spacecraft journeyed past the boundaries of our solar system, they offered an unparalleled chance to examine cosmic rays within an environment unaffected by our planet's magnetic field. A pivotal early discovery occurred when Voyager 1 crossed the heliopause and registered a dramatic spike in the quantity of cosmic rays. This observation confirmed that our solar system exists as a kind of bubble, partially shielded from the intense radiation that permeates the rest of the galaxy by the Sun's sphere of influence. This protective shield, known as the heliosphere, doesn't block these particles uniformly. The intricate structure of the Sun's magnetic field, which constantly twists and shifts with its rotation, creates vulnerabilities. The instruments aboard the Voyager probes revealed that some cosmic rays are able to exploit these weak points and penetrate deep into the solar system, a fact that carries significant weight for assessing the radiation hazards future deep space explorers might face. The data gathered has also illuminated the distribution of these rays, showing that instead of being evenly dispersed, they seem to travel in waves and dense clusters. Scientists theorize this is a direct result of magnetic fields, which guide the trajectories of these charged particles, forcing them to spiral along the field lines rather than move in straight paths, and creating complex patterns we are still trying to understand. While researchers anticipated that Voyager would encounter a magnetic environment in interstellar space vastly different from our Sun's, the spacecraft uncovered a surprising connection. It appears the interstellar magnetic field remains closely linked to the solar field, instead of having a distinct boundary, possibly through a process called magnetic reconnection, where field lines break apart and reform, releasing tremendous energy and challenging existing theories. These observations have helped us refine our understanding of how magnetic fields sculpt the universe. Although invisible, they exert a profound influence, directing the flow of cosmic rays, shaping the formation of stars, and even dictating the structure of galaxies. By bending the paths of cosmic rays, these fields effectively disperse their energy, mitigating localized radiation damage and distributing their effects more evenly. The Voyager missions have also provided fresh insights into the cosmic ray sea, the ever-present background radiation that fills interstellar space. By analyzing the energy levels and origins of these rays, scientists are piecing together a more detailed picture of the violent celestial events that spawn them. Some particles detected seem to have come from recent supernovae in our own galactic vicinity, suggesting that past stellar explosions could have played a role in the formation of nearby star systems, potentially including our own. Beyond the Sun's immediate influence, Voyager has also picked up on signals from distant shock waves generated by far more massive cosmic phenomena, such as the blast waves from supernovae rippling through the interstellar medium. A critical long-term application of studying these particles is to improve the safety of space travel, as high-energy cosmic rays pose a serious threat to human health by damaging DNA and elevating cancer risks. The data collected by the Voyager probes are essential for helping scientists comprehend how these rays behave in deep space, which is the first step toward developing more effective shielding for future missions. If humanity is to ever journey beyond the Moon and Mars, mastering how to counteract the effects of cosmic radiation will be absolutely crucial for our survival. Beyond the practicalities of human exploration, cosmic rays may also hold the answers to some of the most fundamental questions about the universe. Some of these particles possess energies that vastly exceed anything we can generate in our most advanced particle accelerators on Earth. It's believed they originate from the most extreme cosmic environments, such as the immediate vicinity of black holes or the remnants of hypernovae, offering you a potential glimpse into physics beyond our current understanding. What was once considered a featureless void, the interstellar medium is now understood to be a dynamic and highly structured environment. It is filled with complex interactions that shape everything from planetary systems to the birth of stars. Consequently, cosmic rays are no longer seen as mere high-energy static, but as vital clues to the universe's most powerful explosions and forces, while the magnetic fields that guide them reveal a hidden cosmic architecture. In this grand cosmic structure, you find that gravitational interactions in deep space reveal gravity as the universe's unseen architect, dictating the motion of planets, stars, and entire galaxies. Every single object, from the smallest asteroid to the most colossal black hole, exerts a gravitational influence on its surroundings, and the delicate equilibrium of these forces determines everything from the stability of a solar system to the very formation of galactic clusters. You can see this principle at work in our own cosmic neighborhood, where Earth and the neighboring planets trace predictable elliptical paths around the Sun. This celestial dance is a motion that was first mathematically described by Johannes Kepler back in the 17th century. The laws of planetary motion, which were later validated by Isaac Newton's theory of gravity, revealed that celestial orbits are the outcome of a continuous gravitational tug-of-war. You see, while the Sun's immense gravity constantly attempts to pull the planets inward, their own forward momentum keeps them locked in these stable, orderly paths. When celestial bodies, like planets or moons, approach one another, their gravitational fields engage, often subtly modifying their trajectories. These gravitational encounters can result in minor, temporary adjustments to speed and direction, or they can trigger more profound, lasting alterations to an object's course, sometimes even ejecting it from its home system to wander through deep space. One of the most compelling illustrations of these gravitational dynamics is what's known as orbital resonance. This phenomenon happens when two or more orbiting bodies apply regular, periodic gravitational force on each other, locking them into a stable and predictable pattern. For instance, you can observe this with Jupiter's moons Io, Europa, and Ganymede, which are held in a precise resonance. For every 4 orbits Io completes, Europa makes exactly 2, and Ganymede finishes precisely 1. This gravitational timing is crucial for maintaining the stability of their orbits, and you can find similar resonances shaping planetary ring systems. The iconic rings of Saturn, for example, are sculpted by the gravitational influence of its many moons. Some of these smaller moons function as shepherds, their gravity corralling the ring particles into place, while others carve out distinct gaps by gravitationally disrupting the regions they pass through. In binary star systems, you find 2 stars orbiting a shared center of mass, held together by their mutual gravitational pull. Some of these pairs involve stars of comparable size engaged in a relatively stable cosmic dance. In other, more dramatic systems, the powerful gravity of a much larger star actively siphons material from its smaller companion, which can form swirling accretion disks as the stolen matter spirals inward. Within entire galaxies, stars are guided by gravity as they orbit the galactic center, influenced not only by visible matter, but also by the pervasive, invisible presence of dark matter. In fact, the unexpectedly high rotation speed of galaxies was one of the first major clues pointing to dark matter's existence, as the visible mass alone couldn't account for the necessary gravitational force. Spacecraft navigating our solar system often depend on gravitational assists to boost their speed and alter their flight paths. By executing a close flyby of a planet, a probe can leverage that planet's gravity to accelerate and change direction, all without using extra fuel. This very technique was essential for missions like Voyager, Cassini, and New Horizons to reach their distant targets. The entire history of our journey into space has been shaped by the evolution of spacecraft instrumentation. From the first satellites to our most sophisticated deep space probes, the advancement of these instruments has always dictated which questions we could ask and which cosmic riddles remained just beyond our grasp. Each new generation of technology sharpens our vision, giving us a more detailed understanding of alien worlds and the fundamental laws of the cosmos. The earliest instruments sent to space were built with one primary objective: to function and survive. The initial satellites of the 1950s and 60s, such as Sputnik and Explorer 1, were equipped with only basic sensors for detecting radio waves, measuring temperature, and monitoring Earth's magnetic field. These simple tools had to be compact, light, and fully autonomous, providing our first crucial data from beyond the atmosphere. As space agencies refined their methods, the instruments they deployed grew far more complex. The Pioneer and Mariner programs of the 1960s and 70s represented humanity's first ventures to explore other planets, carrying early cameras, spectrometers, and magnetometers. These devices gave us our first close-up images of Mars and Venus and revealed their chemical compositions by analyzing light, fundamentally changing our view of the solar system. The arrival of digital imaging in the latter half of the 20th century truly transformed spacecraft instrumentation. The Viking landers, which reached Mars in the 1970s, were outfitted with the first high-resolution cameras that used digital sensors instead of film. This breakthrough allowed images to be sent directly back to Earth, setting the stage for all modern planetary exploration. A parallel innovation that proved just as crucial was the miniaturization of electronics. Early space probes were constrained by bulky, power-intensive components, which severely limited the number of scientific tools they could carry. However, ongoing technological progress has enabled the development of smaller, more efficient instruments, allowing us to pack more investigative power into every mission. The Galileo probe, which ventured to Jupiter in the 1990s, was outfitted with a compact suite of instruments that measured radiation, temperature, and atmospheric makeup with remarkable precision. This ability to load multiple sensors onto a single craft enabled a far more complete understanding of planetary environments, a significant leap from early missions that needed constant supervision and real-time adjustments from engineers on Earth. In contrast, modern spacecraft possess onboard computers that grant them the power to make autonomous decisions. A prime example can be seen in the evolution of rovers, from Sojourner in 1997 to Spirit, Opportunity, Curiosity, and Perseverance. These explorers are all equipped with sophisticated navigation and analysis systems, which allow them to recognize noteworthy geological features, choose targets for closer inspection, and even shift their scientific priorities based on incoming data. Another profound advancement has been the capability to remotely gather and scrutinize physical materials. The OSIRIS-REx mission, which embarked in 2016, adeptly collected samples from the asteroid Bennu using a robotic arm fitted with various instruments. This marked a departure from earlier missions that depended solely on remote sensing, as this spacecraft successfully returned matter to Earth for intensive laboratory examination. The upcoming Artemis program, which intends to return humans to the Moon, will expand upon this method by using robotic instruments to pinpoint promising sample locations before the astronauts even arrive. This stands in stark contrast to the initial period of space exploration, when sluggish data transfer rates severely limited the quantity of information that could be relayed home. The Deep Space Network, a global array of large radio antennas, proved essential for dramatically improving communication with distant probes. Refinements in radio signal processing have led to higher resolution imagery, more detailed spectroscopic analyses, and even live data feeds from landers and rovers. The development of laser communication systems, which are currently being tested on several missions, promises to elevate data transmission speeds even further. An equally transformative breakthrough has been the capacity to detect and study invisible wavelengths of light. While standard cameras capture the visible spectrum, a great many of the most crucial space discoveries have emerged from observing other regions of the electromagnetic spectrum. Infrared telescopes, like those on the Spitzer Space Telescope and the James Webb Space Telescope, can look through obscuring clouds of dust to reveal areas where stars are born and to study the atmospheres of exoplanets. At the same time, ultraviolet and X-ray instruments, like those aboard the Chandra X-ray Observatory, yield information about high-energy cosmic phenomena such as the behavior of black holes and the remnants of supernovae. Our capacity to view the cosmos across this wide range of wavelengths has fundamentally reshaped our knowledge of how galaxies, stars, and planetary systems form and change. Adding to this, gravitational wave detectors like LIGO, the Laser Interferometer Gravitational Wave Observatory, can sense tiny disturbances in spacetime that are caused by distant cosmic collisions. These observations work in tandem with traditional telescopes, presenting a completely new avenue for studying the most extreme events in the universe. Meanwhile, neutrino detectors in space, though still in their early experimental stages, are being developed to catch elusive particles that travel through matter almost without interaction, which could offer clues to the universe's most energetic processes. The trend toward miniaturization is powerfully expressed in the rise of CubeSats, which are small, modular satellites that can be launched in large groups. These compact spacecraft are fitted with miniaturized versions of conventional instruments, making it possible to conduct frequent and low-cost observations of the space environment. Some CubeSats are even designed to fly in formation with larger missions, offering different perspectives on celestial bodies or relaying data from areas that are difficult to reach. For instance, the Mars Cube 1 mission involved 2 small CubeSats that relayed signals from the InSight lander as it made its descent to the Martian surface. Looking toward the future, quantum sensors are being engineered for new missions, using the principles of quantum mechanics to register the tiniest variations in gravity and magnetic fields. Such technology could enable spacecraft to map the subsurface geology of planets and moons with unprecedented accuracy. Moreover, self-healing materials and instruments based on nanotechnology are also poised to play a significant role, helping spacecraft survive extreme environments and extending their operational lifespans. Every improvement in sensors, cameras, spectrometers, and communication equipment pushes the boundaries of exploration further. As these technologies progress, our ability to investigate deeper into space and find new phenomena will only expand, bringing humanity closer to understanding the universe's most fundamental questions. Unraveling molecular mysteries is key to tracing the origins of life beyond our planet, as the search for extraterrestrial life has long been a major impetus for space exploration. Although telescopes and planetary probes send back stunning images of distant worlds, their most essential work is often conducted at the molecular level. The basic ingredients of life, including amino acids, organic molecules, and complex carbon compounds, are found throughout the cosmos. Figuring out where these molecules are created, how they interact, and if they might spark the emergence of life is one of the most profound scientific pursuits of our era. Deep space missions equipped with highly sophisticated instruments are actively decoding these molecular puzzles, shedding light on the chemical foundations from which living organisms might emerge. The hunt for these molecular precursors to life naturally starts with an examination of the chemistry of planets and moons right here in our solar system. Mars has become a primary target for these investigations, where a succession of rovers and orbiters have scrutinized its surface and atmosphere for the presence of organic compounds. On Mars, the Curiosity rover's sample analysis instrument uncovered a range of organic molecules within the planet's rocks. Although this isn't proof of life itself, it does indicate that the fundamental ingredients for life were present on Mars billions of years in the past. To advance this investigation, the Perseverance rover is now in Jezero Crater, gathering and storing rock specimens for future, highly detailed analysis back on our own planet. Yet, the search extends beyond Mars, with Saturn's moon Enceladus emerging as a fascinating target for molecular investigation, as plumes erupting from its subsurface ocean hint at potentially habitable conditions. What you might perceive as the void of space is, upon closer inspection, anything but empty. In truth, the interplanetary expanse is teeming with countless objects, nomadic celestial bodies that serve as quiet observers of our solar system's formation and development. Among these, asteroids and comets are particularly significant, as these travelers follow complex trajectories through the cosmos that can occasionally bring them uncomfortably close to our world. Let's journey back in time roughly 4 billion years. to when a colossal cloud of gas and dust was contracting under its own gravitational pull. From the heart of this swirling mass, our young sun ignited, while the surrounding material began to clump together to create the planets. This era was a tremendously turbulent and disorderly period, much like a vast celestial construction zone, and the asteroids we see today are the unused rubble from that epoch, the raw materials that never became part of a larger world. The majority of these cosmic remnants, with sizes varying from several meters to hundreds of kilometers in diameter, reside in what is known as the main asteroid belt, situated between the orbital paths of Mars and the colossal planet Jupiter. You should dismiss any science fiction imagery of a densely packed field of rocks. The reality is that the asteroids are separated by immense, million-kilometer distances. Despite this emptiness, their population is vast, numbering in the hundreds of thousands confirmed, with potentially millions yet to be found, including giants like the dwarf planet Ceres and the nearly spherical Vesta and Pallas, though most are simply irregularly shaped fragments of rock and metal. Jupiter's immense gravitational force is the key factor shaping the destiny of everything within the asteroid belt. The gas giant's powerful influence not only prevented the raw materials from forming a new planet, but also continuously agitates the asteroids, occasionally ejecting them from their stable paths onto highly stretched-out orbits. This process sends some of these space rocks on epic voyages into the inner solar system, where they may intersect the orbits of Mars, Earth, Venus, or Mercury, earning them the designation of near-Earth asteroids, objects that are both scientifically fascinating and potentially hazardous. Asteroids, however, are not the sole nomads roaming our cosmic vicinity. They are joined by comets, which are fundamentally different in their makeup. Whereas asteroids are primarily composed of rock and metal, comets are often described as cosmic dirty snowballs, consisting of a mix of frozen gases like water, methane, ammonia, and carbon dioxide, all bound with dust. These objects hail from the coldest, most remote parts of our solar system, originating in the Kuiper belt beyond Neptune's orbit, a region also home to the dwarf planet Pluto, or from the even more distant and theoretical Oort cloud, a vast sphere of icy bodies that surrounds our entire solar system. From these frigid, dark frontiers, gravitational nudges from passing stars or collisions can dislodge a comet, sending it on a long trajectory toward the sun. As it gets closer to our star, the comet's frozen core heats up, causing its ices to turn directly into gas and release trapped dust, creating a massive glowing envelope around the nucleus known as the coma. Subsequently, the sun's radiation and solar wind push this material into two distinct tails, a straight bluish ion tail that points directly away from the sun, and a broader, curved yellowish dust tail that trails along the comet's orbital path. The breathtaking sight of a tailed guest in the night sky has captivated, and at times terrified, humanity for millennia. Similar to asteroids, comets can also intersect with Earth's orbit and become near-Earth objects, though they typically travel at much greater velocities because of their highly stretched-out paths. This illustrates that our solar system is an active and evolving place, filled with innumerable asteroids and comets, nomadic relics of creation, in perpetual motion. The study of their origins and trajectories is essential for both appreciating the universe's majesty and mitigating its potential threats. If you want to comprehend the immense energy released during cosmic collisions, you need only observe our closest celestial companion, the Moon. Devoid of air and geologically inert, its surface is covered with an uncountable number of craters, ranging from small depressions to massive basins spanning hundreds of kilometers. The Moon effectively serves as a gallery of cosmic violence, perfectly preserving the evidence of impacts stretching back billions of years, with every crater marking a past encounter with an asteroid or a comet. This raises an obvious question. Why doesn't Earth, occupying the same cosmic neighborhood, display a similarly cratered face? The explanation is rooted in the dynamic processes that define our world, beginning with its substantial atmosphere, which acts as our first and most dependable line of defense. You might not realize it, but the Earth has a formidable defense system. Most smaller meteoroids, those just a few meters across, completely incinerate upon entering our atmosphere, blazing across the sky as meteors, or what you might call shooting stars. Only the more massive objects possess the momentum to break through this protective shield and continue their journey toward the ground. Even when a substantial object does manage to strike the surface and excavate a crater, our planet has powerful geological forces that work to erase the evidence. The relentless processes of erosion, including wind, water, and ice, steadily wear down the landscape, gradually smoothing over the scars of even colossal impact events. Furthermore, with about 70% of our world covered by oceans, many ancient wounds are effectively hidden from view beneath the waves. Finally, the very crust of our planet is in constant motion. Composed of shifting tectonic plates, ancient ocean floors, along with any craters they hold, are continuously dragged down into the mantle in what are known as subduction zones, while new crust is formed elsewhere. These dynamic processes, from continental collisions that build mountains to the slow erosion that wears them down, all work in concert to heal the planet's cosmic injuries, effectively wiping the slate clean. However, this planetary regeneration doesn't mean Earth has been spared from cosmic bombardment. It simply means you have to know where to look for the traces. Let's journey back in time to the morning of June 30th, 1908, in the desolate Siberian taiga, near the Podkamenaya Tunguska River. On that day, the sky was suddenly torn apart by a light more blinding than the sun, followed by a tremendous explosion heard for hundreds of kilometers. A ferocious shockwave erupted, flattening more than 2,000 square kilometers of forest, with trees felled in a radial pattern, their roots all pointing toward the blast's center. Eyewitnesses reported seeing a towering pillar of fire and smoke ascending into the sky. Yet, when scientific expeditions finally reached this remote location decades later, they discovered no impact crater, leaving behind a perplexing mystery. The most widely accepted explanation for the Tunguska event is that a celestial body, likely a stony asteroid or an icy comet nucleus, detonated in an enormous airburst several kilometers above the ground. The object itself was completely vaporized in the atmosphere, but it unleashed an amount of energy equivalent to a massive thermonuclear bomb, serving as a chilling reminder that a cosmic intruder can unleash widespread devastation without ever touching the Earth's surface. Now, let's shift our focus to a far more ancient and calamitous event that left an indelible mark on the history of all life. Around 66 million years ago, at the transition between the Cretaceous and Paleogene periods, a mass extinction event annihilated approximately 75% of all species on the planet. This cataclysm famously brought an end to the dinosaurs, who had dominated the terrestrial world for over 150 million years. For many years, the cause of this global catastrophe was an enigma. The breakthrough came when scientists found a thin, worldwide layer of clay from that exact period, containing unusually high levels of iridium, an element scarce in Earth's crust, but abundant in asteroids. This discovery provided compelling evidence for an asteroid impact. But one question remained. Where was the crater? It took considerable time to find the impact site. Using gravitational and magnetic surveys, researchers eventually detected a massive ring structure, about 180 kilometers in diameter, buried deep beneath sediments on the Yucatan Peninsula in Mexico and the floor of the Gulf of Mexico. This was the Chicxulub crater, and calculations confirmed it was formed precisely 66 million years ago by the collision of an asteroid at least 10 kilometers wide. An impact of such staggering proportions would have triggered truly global consequences, perfectly explaining the mass extinction event. Scientists continue to find other telltale signs of ancient collisions, such as specific minerals like shocked quartz or stishovite, which can only form under the extreme pressures of an impact. They also find tektites, which are glassy beads of ejected molten rock, and other anomalies within geological layers. Every crater we uncover, and each trace of a prehistoric impact, serves as a lesson from our deep past. They remind us that our world exists within a vast and dynamic cosmic environment, where such events, while infrequent on a human timescale, are a fundamental part of the planet's long and violent history. The scarred face of the moon and the hidden wounds of Earth both testify to forces capable of reshaping entire worlds. Imagine looking up into a perfectly clear sky, only to see a new, brilliant star materialize out of nowhere. It rapidly intensifies, soon outshining the midday sun itself. This isn't a star. It's a harbinger of destruction, a large asteroid or comet plunging into the dense layers of the atmosphere at tens of kilometers per second. The immense air resistance in front of the object compresses and heats the air to unimaginable temperatures, causing its surface to glow white-hot. The object transforms into a colossal fireball, a blazing streak across the heavens, leaving a trail of smoke and a deafening roar like the sound of 1,000 jet engines combined. For anyone positioned near its trajectory, the sight of this celestial monster hurtling toward the ground would likely be their last. Should the object be large and durable enough to survive its fiery atmospheric descent, it will ultimately reach the surface. And at that moment, an almost inconceivable amount of energy built up over its cosmic journey is released in an instant. The object's kinetic energy is violently converted into other forms, unleashing an explosion many times greater than any nuclear weapon ever devised by humanity. The immediate effect is a blinding flash and an intense pulse of heat that incinerates everything, living or not, for many kilometers around the impact site. For a brief moment, the temperature at the epicenter soars to tens of thousands of degrees, rivaling the surface of the sun. This inferno is immediately followed by a devastating shockwave. Not merely a powerful wind, but a supersonic wall of compressed air expanding outward in all directions, moving much faster than the speed of sound, and obliterating everything in its path. An unseen barrier of immense pressure obliterates everything it encounters. Structures are pulverized into dust, entire forests are splintered like matchsticks, and even heavy industrial equipment is ripped to pieces. This devastating shockwave is powerful enough to circumnavigate the globe multiple times before it dissipates, with its destructive power felt across enormous distances from the point of impact. At the very same moment, the atmospheric shock wave expands. A seismic event of inconceivable force originates deep within the Earth's crust. The point of collision transforms into the epicenter of a mega-earthquake, potentially registering a magnitude greater than 10 or even 11 on the Richter scale, depending on the size of the impacting body. These seismic vibrations propagate through the entire planet, setting off secondary quakes, landslides, and avalanches in the farthest reaches of the globe. The creation of the impact crater commences instantly at ground zero. The immense pressure from the collision compacts and flash vaporizes the bedrock directly beneath it. This is followed by a violent expulsion, launching billions of tons of molten rock, dust, and vapor, tens or even hundreds of kilometers into the sky. This material forms a distinct rim around the resulting chasm and spreads debris across immense territories, leaving behind a deep, temporary cavity that eventually collapses to form a complex crater, often with a central peak and ring-like structures. Should the asteroid strike the ocean instead of land, the resulting devastation is different, yet equally horrifying. The immediate superheating and vaporization of a vast quantity of water triggers a steam explosion of cataclysmic power. The most significant outcome, however, is the creation of a mega-tsunami, waves far beyond anything generated by even the most powerful earthquakes. An impact of this nature can create waves hundreds of meters or potentially kilometers tall near the epicenter. These mountains of water traverse the ocean at the velocity of a commercial jet, remaining almost undetectable in deep water, only to swell to gargantuan proportions as they reach the shallows. They then slam into continental coastlines thousands of kilometers away, surging deep inland to obliterate everything and contaminate fertile soils with salt for many years. Naturally, the magnitude of the devastation is contingent upon the cosmic object's size, velocity, impact angle, and makeup. A minor asteroid, such as the one responsible for the Tunguska event, or the one that detonated over Chelyabinsk in 2013, would lead to considerable local damage, but would not escalate into a worldwide disaster. In contrast, an object measuring several kilometers across could annihilate a region comparable to a small nation and initiate severe global consequences. A denser metallic asteroid would likely survive to strike the surface, creating a more profound crater and a stronger seismic shock, whereas a less cohesive rocky or icy body might detonate higher up, producing a more potent atmospheric blast wave. Whatever the specifics, a collision with a large celestial body unleashes immediate, absolute, and inconceivable ruin upon the impact zone. A localized apocalypse that is but a prelude to far graver outcomes for the planet. The instant annihilation at ground zero, as terrible as it is, only sets the stage for more drawn-out and sinister effects that will influence the entire globe and reshape life's trajectory for millennia. The disaster is far from over when the shock wave subsides and the dust settles. It initiates a cascade of global shifts whose repercussions will be felt for an exceptionally long time. Picture billions of tons of pulverized rock, soot, and dust being propelled high into the stratosphere, an atmospheric layer where commercial jets fly and weather events are too scarce to rapidly cleanse the air. This thick shroud of microscopic particles spreads to envelop the globe, forming an impenetrable shield against sunlight. The very rays from the sun that provide our world with life-giving warmth are effectively blocked, unable to pierce this newly formed atmospheric veil. This leads to a phenomenon that scientists term an impact winter, often likened to a nuclear winter, which is a prolonged phase of planetary cooling and darkness. Earth's surface is submerged in a persistent twilight, or even absolute blackness, for months or potentially years, until the finest dust and aerosol particles gradually return to the ground. Consequently, global temperatures would drop catastrophically, perhaps by tens of degrees Celsius, transforming even the warmest tropical regions into frigid, Arctic-like environments. For terrestrial life, which is almost entirely dependent on photosynthesis, this scenario is tantamount to a death sentence. All plant life, from the ocean's microscopic algae to towering forest trees, needs sunlight to create energy. Under a veil of global darkness, photosynthesis ceases entirely, causing the planet's vegetation to wither and perish. The ecosystems that rely most heavily on a steady supply of solar energy are the first to collapse. In the seas, the phytoplankton that serve as the base of the marine food web and generate much of our oxygen will die out, followed swiftly by the zooplankton that consume them, and then in turn the fish, marine mammals, and the rest of ocean life. A parallel process of devastation occurs on land. The widespread death of plant life condemns herbivores to starvation, and the predators that hunt them are not far behind on the path to extinction. Entire food webs, developed over millions of years, are shattered in a very short time. The only survivors are those species adapted to endure extended periods of cold and famine. Creatures that can subsist on decaying matter, dig for roots, or enter a state of hibernation. Researchers theorize that this exact sequence of events took place 66 million years ago, following the Chicxulub asteroid impact, which resulted in the mass extinction event that eliminated the dinosaurs and innumerable other forms of life. However, the impact winter represents just one of the worldwide repercussions. The immense energy unleashed by the collision, combined with superheated rock fragments blasted from the crater, would re-enter the atmosphere on ballistic paths across the globe, likely igniting planet-wide wildfires. This would cause millions of square kilometers of forests and grasslands to go up in smoke, pumping even more soot into the air, which would intensify the impact winter and release staggering quantities of carbon dioxide. Furthermore, the vaporization of enormous rock volumes, particularly if the impact site is rich in sulfur or carbonate deposits like limestone, or is in the ocean, injects sulfur and nitrogen oxides into the stratosphere. These compounds mix with atmospheric water to create sulfuric and nitric acids, which then fall as acid rain. Such precipitation poisons soils and aquatic ecosystems, delivering another devastating blow to surviving vegetation and marine life, while fundamentally altering the chemistry of the oceans. Even after the skies clear and sunlight once again reaches the surface, the climate might not recover quickly. The colossal amount of carbon dioxide released from the impact and the subsequent fires could amplify the greenhouse effect, leading to a prolonged period of global warming that poses entirely new survival challenges for the planet's ecosystems. An impact from a large asteroid is therefore not a singular, localized disaster. It's the catalyst for a chain reaction of interconnected global catastrophes, including darkness, cold, fire, acid rain, and enduring climate shifts that challenge the resilience of the entire biosphere and could permanently change the course of life on Earth. Upon realizing that a threat of this magnitude could arise from the depths of space, humanity chose not to passively await its fate. Instead, this awareness has spurred remarkable advancements in science and technology, focused on safeguarding our world. We are now in an age where astronomers serve as the sentinels of Earth, diligently scanning the cosmic expanse for celestial bodies whose trajectories might cross our own. This undertaking is monumental in scale. Imagine the challenge of spotting relatively small, non-luminous objects hurtling at incredible velocities against the infinite, star-dusted backdrop of space. To accomplish this, specialized telescopes and automated sky survey systems are in operation around the globe. Every clear night, these instruments systematically examine designated areas of the sky, capturing images and comparing them against earlier ones. Sophisticated computer algorithms then analyze this data, hunting for any moving points of light that could be undiscovered asteroids or comets. When a potential candidate is identified, the information is relayed to other observatories to be verified and tracked. Scientists meticulously record the object's position over time to calculate its orbit around the Sun with extreme accuracy, a task comparable to predicting a stone's flight path, but on a solar system scale, with objects millions of kilometers away. These calculations help determine how close the body might approach Earth and assess the likelihood of a future collision, with special focus on potentially hazardous objects that are large enough and have orbits that bring them near our planet. Fortunately, at this moment, no known large object is on a definite collision course with our planet in the near future. Nevertheless, the search and cataloging efforts are ongoing, because there is always a possibility of finding a new cosmic visitor, or discovering that a known object's refined orbit is more threatening than initially believed. But what would happen if, one day, we did find a dangerous object on an unavoidable path toward Earth? We are far from helpless. Scientists and engineers across the globe are actively developing and testing various planetary defense strategies. The core principle isn't to obliterate the asteroid, an act that could create a hazardous swarm of unpredictable fragments, but rather to alter its trajectory. The goal is to apply a subtle push that over the months or years of its remaining journey is enough to make it miss Earth entirely. One of the most well-developed and successfully demonstrated techniques is the kinetic impactor. The concept is straightforward. A purpose-built spacecraft, acting as a kamikaze probe, is sent to collide with the asteroid at high velocity. The momentum from this impact, much like one billiard ball striking another, slightly changes the asteroid's speed, and as a result, its orbital path. NASA's Double Asteroid Redirection Test, or DART, mission brilliantly proved this concept by successfully altering the orbit of the small asteroid Dimorphos as it circled its larger companion Didymos. A second promising technique is the gravity tractor, which leverages the fundamental principle that any object with mass exerts a gravitational pull. By positioning a sufficiently massive spacecraft near an asteroid, and using its engines to maintain a fixed distance, the gentle but constant gravitational tug between the two bodies will gradually and reliably steer the asteroid from its original course. While this approach takes longer than a kinetic impact, it offers a more delicate and precise method of orbital manipulation. Beyond these, other more unconventional ideas are being explored. These concepts include using concentrated laser or solar energy to vaporize surface material from the asteroid, which would generate a reactive thrust. Another idea involves painting a portion of the asteroid's surface to change how it absorbs and radiates heat, thereby altering the subtle pressure from solar radiation through what is known as the Yarkovsky effect, and slowly shifting its path over time. In the most severe scenarios, involving exceptionally large celestial bodies or minimal warning time, experts have even contemplated the deployment of nuclear devices. The strategy wouldn't involve a direct impact on the asteroid's surface. Instead, the device would be detonated at a calculated distance. This would unleash a powerful wave of radiation, instantly vaporizing a portion of the asteroid's exterior and generating a significant propulsive force to alter its trajectory. However, this approach is riddled with substantial complexities and potential dangers, which is why non-nuclear alternatives are overwhelmingly favored. The likelihood of a truly massive asteroid, one capable of triggering a worldwide disaster, striking within our lifetimes or even over several centuries, is exceptionally small. Despite these long odds, the possibility is not entirely zero, which necessitates a proactive stance. For this reason, maintaining constant surveillance, refining our methods for detection and tracking, advancing and field testing planetary defense systems, and fostering global collaboration are all indispensable components of our security. Investigating asteroids and comets to grasp the threats they might represent isn't a cause for alarm, but rather a summons to responsible action and the pursuit of knowledge. This work serves as a powerful reminder that you and I inhabit a cosmos that is perpetually in motion and constantly evolving. Our duty extends beyond simply marveling at its splendor. We are also tasked with deciphering its fundamental principles to secure a safe future for our one-of-a-kind and delicate planet. By stepping into the role of Earth's protectors, we advance our exploration of the cosmos and come to better understand our own significance within it.